Hi, I'm Josh Lothringer. I'm a second-year grad student at the University of Arizona, and I'm working on transit spectroscopy using the Hubble Space Telescope to look at a special demographic of the super-Earths and sub-Neptune exoplanets. So they're some of the smallest exoplanets that we can look at right now. If you look at plot A there, it's a signal-to-noise versus planet radii. So these are some of the best signal-to-noise planets that we can look at right now that are also fairly small. What's interesting about these super-Earth and sub-Neptune exoplanets is that they can span a wide range of compositions. Plot B here is radius versus mass, but also with some contours of different possible compositions. So you can go from Earth-like planets to 10% helium and hydrogen planets. And what we're hoping to do is with transit spectroscopy we can characterize the atmospheres and then maybe say something about this transition. Can I get this next slide? So here's some preliminary light curves. One of the planets we're looking at is 55 Cancri E. It's got a transit depth of only 0.05% of the host star's light, but the exciting thing is we're getting down to precisions of tens of parts per million. So hopefully we can say something about what these atmospheres are made of. So the observations began in late last year and will continue until early next year. And so hopefully we can say something about this special transition between gas-dominated planets and more Earth-like planets.
Hi, I'm Kat. I just finished my first year at UC Santa Cruz, and last night it occurred to me that exoplanet atmospheres are like cakes. We want to know what ingredients went in, how much of it, and how long did it bake for. So to understand a planet's atmosphere well is to get a taste of its formation condition, evolution history, and internal structure. And when we observe a planet, sort of like on the top left plot, if we combine multiple instruments, we can get the overall shape of its emission spectrum. And to recover information from the spectra, we do what we call retrieval. And that just uses statistics to figure out what set of chemical abundances and thermal structure can explain what we observe. And in the future, with telescopes like the James Webb Space Telescope, our data will be more numerous and the error bars will be smaller. However, a retrieval still only just gives us one set of parameters, and when in reality, it's a spectrum generated by a complex 3D atmosphere. With that said, regardless of precision, when we do our retrievals, we really want to ask what limits our accuracy. So what we're trying to do is interpret our interpretation of the data. But to do that, we will start creating more sophisticated 3D atmosphere models, incorporating different opacity databases, covering different wavelength ranges, different viewing geometries. And after that, we will explore biases in our 1D retrievals. Okay. So what that means is, say we have a planet that is uniform everywhere, but it has a hotspot in the center. When we retrieve on it, we want to ask how biased is the retrieve values towards the information contained in the hotspot. And after we do that, we want to apply our retrievals on our 3D models and compare whether or not we do better in our retrievals for different wavelength ranges, signal-to-noise ratios, and so on to help us plan for future observations. If you want to learn more, come to poster number 8.
Hi, I'm Ryan. I'm a first-year student at the University of Oxford, and so I've actually been working on brown dwarfs. I don't think anyone else has been here. Well, you might have, but you don't seem to be giving a presentation. And I'm quite surprised actually because, I mean, compositionally, in terms of like structure and gases and stuff, brown dwarfs are actually very similar to exoplanets. Well, gas giants. And here's a sort of diagram here. You can see the cloud structure is actually very similar. And my PhD is sort of exploring the comparison between the atmospheres of giant planets and brown dwarfs. And if you want to. Yeah, and I've actually been sort of getting into the nitty-gritty of this. And in radiative transport models, normally we use line lists that provide data about the gases so we can calculate opacity. But that is usually in terms of the Earth, because the data for atmospheric retrievals usually comes from decades of Earth research, and this means that we're sort of underestimating some things or overestimating some things when we use the same data for gas giants and brown dwarfs. And so I've been looking into the differences between the pressure broadening, in particular, for comparison between air and H2/HE dominated atmospheres. And I've been investigating this with our retrieval code, which is briefly explained by this equation. And yeah, if you want to know more about that, I have a poster, because I obviously can't go into very much depth. So yeah, thanks.
Hi, I'm Daniel Thorngren, and I'm from UC Santa Cruz. And I have been doing structure evolution models of giant planets to try and figure out their bulk metallicities, which is to say how much heavy elements by mass are inside them. I've been focusing my models on the cooler giants because in those planets, the radius inflation effect is not occurring to a substantial degree, so I don't have to make any assumptions about how that effect works, which is great because I have no idea what I would assume. Now, I'm not the first person to do this, but we've discovered quite a few more planets in that region. So I'm going back and seeing if what we learned before holds up and if there's anything else we can discover. How do I? No, you're doing it. Cool. All right, so I see the expected effect that, well, I think you would expect it. As the planet mass goes up, you have more heavy elements, but less of the total mass by fraction is heavy elements. If you take into account the star's metallicity, the fraction of metals in the planet relative to the fraction of metals in the star, it correlates pretty well with planet mass, and that's the thing on the left, or at least, well, pretty well given our error bars. On the flip side, on the right here, I see that before we had thought that there was a pretty direct connection between the parent star metallicity and the total heavy elements in a planet, and it doesn't look like that's holding up. We keep adding more planets with low parent star metallicities, and they keep filling in all the wrong places. So we'll see as more planets come in, but it doesn't look like that's happening. All right, thank you.
Hello, my name is Angie Wolfgang. I just graduated from UC Santa Cruz, and I'm going to Penn State in October for an NSF postdoc. So my work lies right at this intersection of theory and observations, developing the necessary tools in order to do this kind of a comparison that this entire workshop is about. So I wanted to give you an example of this, in a real-life example. Okay, so one of the papers that I wrote for my thesis, me and my collaborator, Eric Lopez, we derived a composition distribution for Kepler's sub-Neptune planets. So you can see a mass radius distribution generated from that composition distribution right here. And what you can see is that there's a wide range of masses at any given radius. So this motivated us, this is from the theory side, this motivated us to look observationally at what we see. So a lot of people have been interested in the mass-radius relationship because it's a very practical thing for all of you who do theory wanting to get masses from the Kepler measurements of radii. But a lot of people have done is they have done deterministic mass-radius relationships, which you can see right here. But as we see, there's an intrinsic spread, and we need to characterize that. So the way that we chose to do this is my work with Leslie Rogers and Eric Ford. We chose to parameterize this spread in terms of probability distribution. So what we did is we fit a hierarchical Bayesian model, which is really the future in this intersection between theory and observations. So if you're interested in this, please come talk to me. I have several papers on the application of this method. These are the posterior distributions you can see for the parameters that describe this mass-radius relationship. And then next slide, please. This is what the mass-radius relationship actually looks like. So you can see the data that we have in the huge error bars, which are no fault of the observers at all. These are really hard measurements to make. But since we're interested in this mass-radius relationship for sub-Neptune planets, we really have to incorporate this. So this is what you see here is a mass-radius relationship. So this paper is on the archive. Please check it out, and if you have any questions, come find me during the week. Thank you.
Hi everyone, I'm Amit Goel, and I come from University of Central Florida. I'm a PhD student there. I'm working in applying machine learning methods to astronomical data. So basically there are several machine learning methods, and what we are trying to do is, I don't know anything about astrophysics or astronomy, so we are trying to blindly take the data and apply it, that what happens if we apply those machine learning algorithms which have been successful in other fields, what we can discover in astrophysics by doing that, or do we need to improve those methods? So what we found, for example, when we applied that some of those methods on exoplanet data, can we go to the next? Yeah, so for example, as you can see, this is Kepler's third law for our exoplanet systems. We extracted 672 observations from the whole catalog, and we plotted it, and then we applied outlier detection algorithms on this. Can we go to the next slide? Yeah, so as you can see that we applied 3 different algorithms, and they all came up with different observations, like some of them totally removed some of the stars which are on the top. So I'm working on this with Professor Montgomery, and I just started working in January, so this was the only work which I could present in this presentation. But the summary is, I can summarize it as that we are trying to find better machine learning algorithms, or a better way of analyzing exoplanets data. Thank you.
Roll up, roll up. Welcome to the Exoplanet Archive. What you're about to see is the world's greatest collection of exoplanets. We have the smallest. We have the biggest. In fact, we have all of them. We have the table of confirmed planets that NASA maintains. We have habitable zone planets. You want them, we got them. We have multiple planet systems. We have one incredible system with 7 planets. You won't believe your eyes. Moving on to the next exhibit. When you've recovered from the first. We have all the Kepler data. You want candidates, we got candidates. We have the pipeline products. If you want to see what the pipeline is doing, we've got them. What else do we have? All right, the very brave. If you want to go behind this curtain over here, we have the actual data. Oh my God, I know it's scary. You want light curves, you want spectra, you want transit spectroscopy. Oh my God, only the truly brave, ladies and gentlemen, please. We also have contributed data. Other people have been brave enough to contribute to our exhibit for everyone to see. Finally, for the insane amongst you, if you want to get hands-on with the truly bizarre, we let you interact with the exhibits. We have plotting, we have periodograms, you can sort, you can filter. It's incredible. So come along today, roll up to the Exoplanet Archive. Thank you very much.